Newton's laws of motion are often presented as dry mathematical tools, but there is a kind of beauty to them that is often overlooked. In this video we're going to talk about Newton's laws from a somewhat more philosophical and historical perspective than is typical. If you're not familiar with Newton's laws, which really form the very bedrock of physics, then I hope by the end of this video you will feel somewhat familiar with them. If you are familiar with them, I hope I can help you here to see them in a fresh light, in a way that perhaps you haven't thought of them previously. Newton first published his book, Philosophiae Naturalis Principia Mathematica, often called simply Principia, in 1687. The book includes his 3 laws of motion and his theory of universal gravitation, according to which the same force that pulls an apple to the Earth is the same force that enables the Moon to orbit the Earth and the planets to orbit the Sun. The book forms the basis of Newtonian mechanics, the first formulation of classical mechanics. In physics, a mechanics is an area of physics that deals with motion, force and speed. Newtonian mechanics views the universe as composed of interacting solid objects, ranging from tiny particles to planets. Newtonian mechanics is known as classical mechanics to differentiate it from quantum mechanics, which was devised much later on, and the theory of relativity, which, although in a sense part of classical physics, represented a significant departure from Newtonian mechanics. In the last video on this channel we talked about determinism, and Newton's laws did a lot to cement the popular idea of the universe as a machine that so many people believe today. Newton's first law of motion is easy to state, but it rests on a great deal of subtle and profound philosophical thought. It says that an object or body either remains at rest or continues to move with constant speed in a straight line unless a force acts upon it. At first glance, this law seems to consist of 2 parts, but it can be viewed as a statement of a principle known as Galilean relativity, combined with an almost commonplace observation. Let's imagine that we place a rock on a table. There's no way that rock is going to move unless someone pushes it or pulls it. In other words, it will remain stationary unless a force acts upon it. And this is the first part of Newton's first law. The idea of a force is an intuitive idea that we arrive at just through our ordinary everyday experiences of pushing things and pulling things. But it took a genius of the magnitude of Galileo Galilei, often known simply as Galileo, to realise that our ordinary intuition about force and moving objects is wrong. Before Galileo, it was often thought that force had to be constantly supplied to keep an object moving, but Galileo realised that, in fact, force is only needed to change how an object moves. Without friction or gravity or wind resistance, a moving object will carry on moving in a straight line with constant speed. Force is only needed to stop it or speed it up or deflect it from its course. In 1632, Galileo gave the first statement of what became known as Galilean relativity. Galileo asked us to imagine ourselves in the hold of a smoothly moving ship, and he asks us whether we could do any kind of experiment in there that would prove it's moving. His answer is no, and this is because movement, as long as acceleration is not involved, is relative. There is simply no matter of fact about whether an observer is moving or not. Imagine you're out in space in a spaceship and an asteroid hurtles past you. Is it you that's moving or the asteroid? Without referring to other objects such as planets and using them to fix your frame of reference, this question does not have an objective answer. You could argue that the asteroid is moving and you are stationary. You could argue that the asteroid is stationary and you are moving. You could argue that both you and the asteroid are moving in opposite directions, flying past each other. Now let's imagine an asteroid flying through space by itself. Newton's first law tells us that it will carry on moving with constant speed in a straight line, unless a force acts upon it. If a force acts upon it, it will speed up or slow down or else swerve off its course. In fact, all of these changes to the previous motion can be considered to involve acceleration. If it slows down, that's negative acceleration. If it swerves from its straight line course, that's acceleration in a different direction to the one it was moving to start with. Imagine now that you are flying in a spaceship next to this asteroid, keeping pace with it. You can consider both yourself and the asteroid to be stationary. Galilean relativity tells us that there is no objective fact about whether you are really moving or are stationary, and there is no experiment you could do that would somehow prove that you are moving without looking at other objects. If you consider yourself not to be moving, then to you, the asteroid also seems not to be moving. If it starts moving, you will conclude that a force has now acted upon it. You regard this as a case of a stationary object starting to move because of a force. A second observer, who considers both you and the asteroid to be hurtling through space, would instead see the asteroid speeding up, slowing down, or swerving from its previous course. So if you think about it, if we assume that non-accelerating motion is relative, the second part of Newton's first law flows naturally from the first. If we believe in Galilean relativity, and if we agree that stationary objects do not start moving without a force acting on them to make them move, then we must conclude that an object moving with constant speed in a straight line will carry on doing that unless a force acts upon it. The fact that Newton's first law seems to come in two halves is really only a consequence of our language, which is necessitated because of the concepts that we habitually use. We regard the distinction between moving and stationary as very important, whereas in truth stationary simply means moving with a speed of zero, and in a way there's nothing particularly special about that from the point of view of the laws of physics. Now I can already imagine physics people jumping down my throat if they happen to watch this video, but I did say in a way. Yes, there's something special about something moving with zero speed, but from another point of view, there isn't. Newton's second law then quantifies how force affects objects exactly. At first glance it is more cryptic than the first, but once you understand the historical context of the law, it becomes a lot clearer. It may be stated as, the force on a body is proportional to the rate of change of its momentum, and in appropriate units it's often rendered as the equation F equals ma, force equals mass times acceleration. To make sense of this, let's dig into the concepts involved. As we've already noted, force is a concept that derives from our everyday experience. We are all used to applying forces to things. That's how we make things move. With Principia, Newton first popularised the term gravity in the sense that it is often used today to refer to an invisible force that pulls things to the earth. The term had previously been used mainly to refer to emotional charge, for example in the phrase, "This is a crime of great gravity." It's true in a sense that Newton invented gravity. Although clearly things fell to the earth prior to Newton, it was Newton who provided us with our most popular conceptual framework for that phenomenon, or at least it was Newton who popularised it. Gravity used in this sense is now a common household word. Even so, it was understood prior to Newton that objects experience a kind of force that pulls them downward. In particular, a man often described as Newton's rival, Robert Hooke, had shown by hanging weights from a spring that the extension of a spring is proportional to the force applied to it. Twice the force means twice the extension. If you hang 2 weights from a spring, the spring extends twice as far as it does with 1 weight. At least, this is true in the middle of the spring's range, when it's neither too compressed nor too extended. In this way, using springs, it was possible to quantify force. Another way to quantify force would be to simply compare a force directly with that produced by a certain number of weights in a balance. And even simpler, if you hold a weight in your hand, you have to apply a certain amount of force to keep your hand from descending. With 2 such weights, you will need twice the force. So this gives us a way of quantifying force. So by the time Newton published Principia, it was very well understood that force could be quantified using springs or weights, not just approximately, but exactly. Acceleration could also be quantified. A ship that gradually increases its speed, running at an average of 1 mile per hour for an hour, and then an average of 2 miles per hour for the next hour, and 3 for the next, and so on, is accelerating at 1 mile per hour. As Galileo and Newton had both observed, an object changes its motion in response to a force, but the question was, how can that change in motion be quantified? Consider the difference between a bus and a car. Even when they move at the same speed, the bus is much harder to stop because its mass is greater. When a bus is moving, there is simply more stuff in motion than when a car is moving. On the other hand, a very fast-moving car may actually be harder to stop than a very slow-moving bus. It's as if objects that are moving quickly or that are more massive contain more motion somehow than objects that are very light or only moving slowly. Newton quantified motion, introducing in Principia a concept that he called quantity of motion or just motion. But Newton's concept isn't popular today. His concept was most similar to what we now call kinetic energy, but Newton's second law is more often stated now in terms of a similar concept which we call momentum. Momentum is a kind of measure of how much motion an object contains. An object considered to be stationary is considered to have 0 momentum. A moving object has a certain momentum which may be easily calculated. If the speed of the object were to double without its mass changing, or if the mass of the object were to double without its speed changing, its momentum would double. We can then say that the rate at which an object's momentum changes is proportional to the force applied to it. Twice the force means twice the rate of change of momentum. It's harder to stop a moving object if that object is big or if it's moving fast than if it's small or slow moving. The larger or faster moving object requires more force to stop it within a given period of time, exactly as if it somehow contains more motion, and indeed the larger or faster object has a higher momentum and a higher kinetic energy. The rate at which the object's momentum will be changed is proportional to the force applied. But this can still be difficult to imagine for anyone who is new to these ideas. In practice, the objects we're familiar with tend to have fairly fixed masses. Mass, which we measure in kilos or pounds or whatever, is a measure of how much stuff an object contains, and this tends to remain somewhat fixed much of the time. If we consider an object of fixed mass, we can say that its acceleration will be proportional to the force applied to it. Twice the force on an object means twice the acceleration. However, it is noticeably much harder to accelerate a heavy object of great mass than a light object of small mass. This is encapsulated by the equation form of Newton's second law, where, in appropriate units, the force on an object is equal to its mass times its acceleration. You can then think of the mass of an object as a kind of property that makes it harder or easier to accelerate. With a given force, an object of small mass like a feather accelerates more rapidly than an object of great mass like a car. This actually has nothing to do with gravity. If you're out in space and you encounter a large asteroid floating around, you're going to have to push much harder or else longer on that to get it moving at a certain speed than you would have to push on a small pebble. We could even think of Newton's second law as providing us with a way to measure mass. We can apply a certain force to an object and see how hard it is to accelerate, disregarding friction. In other words, how fast does it actually accelerate? This concept of mass is known as inertial mass. It's not very convenient to measure mass in this way usually though. We prefer to measure gravitational mass instead. This makes use of the fact that gravity pulls twice as hard on a body as it does on a body that contains half of the mass. The weird thing is, gravitational mass and inertial mass are exactly equivalent. This means that although larger objects are harder to accelerate, it's as though when they are falling, the Earth pulls on them harder, as if to exactly compensate for them being large. And this leads to, as Galileo noted, all objects falling with the same constant acceleration towards the Earth, at least when wind resistance is not a factor. Galileo is supposed to have tested this by dropping objects from the Leaning Tower of Pisa, although that's probably not true. This isn't just true of objects falling on the Earth either, because as Newton saw, all objects pull on each other in proportion to their mass. We don't normally notice this because the effect is very small. It's only really significant for us with very large objects. All objects would also fall at the same rate on the Moon, for example, and there it would be a lot easier to observe because the Moon has no atmosphere to create wind resistance. Finally, we come to Newton's third law, which often used to be stated as every action has an equal and opposite reaction. These days it's common to spell it out a bit more. If a body A exerts a force on a body B, the body B exerts a force of equal magnitude but oppositely directed on the body A. So if A pushes B, B is going to push back on A with an equal force directed in the opposite direction. When you push on an object, it pushes back on you equally hard. Many new students of physics then ask, if this is so, why can you move anything at all if there are two opposite forces that cancel each other out? But these two forces act on different objects. If you push a car, you apply a force to the car which makes the car move. Meanwhile, the car pushes back on you with an equal and opposite force, but you don't move because you're anchored to the ground and you can't move. Instead, the car has to move. Actually, in theory, both the car on the one hand and you and the whole Earth on the other hand do move, but the mass of the Earth is so great that its acceleration will be minuscule and impossible to even observe. This also explains how rockets work. A rocket does not work by pushing against the atmosphere. It can work even on the Moon or in outer space, where there's no atmosphere. When the fuel of a rocket burns, it expands and pushes on the rocket. The rocket meanwhile pushes back with equal and oppositely directed force, causing the burnt rocket fuel to be vigorously ejected from the back of the rocket. After Principia was published, people increasingly thought of the universe as a giant machine. Newton himself suggested, in a preface to Principia, that much of the universe may well obey, if not these exact laws, then analogous laws. Over the following 3 centuries, great strides were made in elucidating the laws that govern chemistry, light, electricity and magnetism. It wasn't until the theory of relativity came along, starting in 1905, and quantum mechanics, which particularly gained traction with the work of Heisenberg in 1925, that serious challenges arose to Newtonian mechanics. Now some may argue that relativity has shown us that Newton's theory is simply wrong, but Gödel's incompleteness theorems in mathematics seem to tell us that any theory in mathematics or physics will necessarily always be incomplete. No theory of physics should be mistaken for reality itself. Every theory is only a model of reality, a map of certain aspects of reality, if you like, and can never itself fully describe reality. No more than a map of Mount Everest can tell us everything there is to know about Mount Everest.